Of course, let's do an example of trying to compute this upper central series. And so the book does some examples, and I'll try to do a different one. Let's try the dihedral group with the square. Because it's a familiar group. And let's see what actually happens. So what is the center of the dihedral group with the square? Well, certainly the identity commutes with everything. And if I remember correctly, the 180-degree rotation commutes with everything. Why? Because RS is always equal to SR inverse. And R squared is equal to its own inverse. So that ends up being true. So then we see, what's D8 modulo its center? Well, it's a group of order 4, so there's only 2 possible choices. And it's probably going to be Z2 cross C2. And one way to see that is because the reflections had order 2 before. They're not going to suddenly have order 4 now. The only element that had order 4 was R. It's going to be sent to an element of order 2 now because R squared is in the center. What is the center here? Well, it's everything. So in this case, we get this is our upper central series, and the nilpotency class is 2. Okay, that wasn't quite as enlightening, but the next example one could try is D16, the octagon. Its center is E and R to the 4th by the same reasoning. Now, that corresponding quotient, if you think about it, it turns out R now has order 4, and it turns out the other relations are the same as they were before. That turns out to be isomorphic to D8. And so now we have some sort of group in the middle here that's actually worth thinking about. What goes here? Well, in the quotient it is R squared, so it should be that one. And so now we see exactly the feature I was talking about. If you multiply R squared by S, you get SR to the negative 2. That is equivalent to SR squared times R to the 4th. So you get commutativity times an element in the center. So we do see that R squared actually is in Z2. By the way, how did I get this? Because what do I need to have happen? I need this group to be the one that when I quotient out by ER to the 4th, I get the center of D8 I had before. Which was, at the level of quotients, was quotient rotation squared. So that's how I knew what to do. This one has nilpotency class 3. And I'm sure you can guess now, as long as I'm taking a dihedral group on a power of 2, I can keep extending and getting higher and higher nilpotency class, and it's a nilpotent group. So it's a conjecture, although it's easy to prove, that d2 to the n is nilpotent. All right, this begs the question of what happens for other even-sided polygons. So let's try d12, so a hexagon. Sorry, I'm following the book's notation where the subscript is the order of the group. So I apologize if, like me, you're used to the subscript being the number of vertices of the polygon. This always throws me off too. So what is the center here? Well, it's e and r cubed. However, d12 mod the center, you can check is d6. That's S3. You can check that S3 is centerless. So unfortunately, this central series ends here. It doesn't actually go all the way to d12. So d12 is not nilpotent. By the same token, whenever d is of the form 2 to the k times an odd number, is not nilpotent. Even though you can prove later that it is in fact solvable. So this is an example of a solvable group that's not nilpotent. So there is in fact a distinction between the two. Note, some of these are actually related to homework exercises in the book, but I thought it was nice to actually go through them because it's good to get an idea how to do these calculations. And yes, we're reaching a point in the course where I'm going to start doing this, where I'm going to prove other stuff from exercises and claims in the book instead of leaving it all as homework, because we're now at a point where it's all stuff that's guaranteed to be new to everybody, so it's much more important to start building the intuition. So another claim that the book makes is that Zi of G is a characteristic subgroup. Which means if you have an automorphism, then it has to send Zi of G to itself. And I leave that as an exercise. So let's see if we can't figure that out. I bet you the proof here, a good proof would be to induct on I. So now that I'm done with this example, let's clear up some room. And so what I can leave for you to figure out is prove that the center is characteristic. That's an interesting exercise worth thinking about. And that would be the base case, I equals 1. We're going to assume that's true. Well, then note what's the definition of zi plus 1? Is defined. So that when you quotient out by zi, you get the center of this quotient. Well, let's let G be an automorphism, or phi be an automorphism. By induction hypothesis, we're going to assume that it fixes the ith central subgroup. We'll then define a homomorphism on this quotient. What do you need to check? You need to check that it's well defined. Well, what does that mean? Well, that means I need to check that if G and G prime define the same coset, then they have the same image under the original automorphism. What does it mean that they define the same coset? That means that G inverse G prime was in the center, or was in this ith central subgroup. So then we have phi of G prime is equal to phi of magically adding in G inverse, or G inverse G prime, which is equal to phi of G times phi of G inverse G prime. If this is in the center, then, oh, well, there's a typo. I don't want something in G, I want something in this quotient. I need to bar, right? So I need to be taking quotients here. Okay, well then, up to quotient, I'm good. It is well defined. So it does actually take elements from this quotient to elements from this quotient. It doesn't matter which coset representative I take. And then, of course, you have to actually prove it's an automorphism by showing it's surjective and injective, or equivalently pointing out that since phi was an automorphism to begin with, it had an inverse, say tau. You could do the same construction to tau to get tau bar, and you can prove that phi bar composed with tau bar is the identity. So I'll skip that step, but it does turn out that this is an automorphism. That's really what I wanted. In particular, because that's an automorphism, it's going to preserve this center. Because this center is a characteristic subgroup. That's the inductive step for I equals 1. This is something I had learned when I had studied graph theory, and this is an example of applying it in a different course. Sometimes you end up studying the base case, and sometimes you end up applying the base case to a different group. So here I'm applying the base case to this quotient group rather than to G. it takes a bit of novelty, or growth to get used to this idea that you can do that, but you can. And so we have that this group is preserved by the subgroup is preserved by this quotient automorphism. Then we go back to what zi plus 1 of g is defined to be. It's defined like that. And so you can ask yourself, is phi of x in zi plus 1 of g? If not, phi of x is in the set difference, which means when I do this quotient operation, it's going to be outside, which would imply that, which would contradict this assumption right here, because x bar is, of course, actually in the center. So since x bar is in the center, phi bar has to keep x bar in the center. Going upstairs, x has to also be kept in z of I plus 1. So we do see that phi of x must be in the ith plus first central group, subgroup, which means that we actually do fix this group as a set. So it's characteristic because we started with an arbitrary automorphism. All right, now we're going to discuss Pgroups with respect to nilpotency. So one of the theorems is that if G has prime power order, G is nilpotent. With class at most n minus 1. By class here, I mean nilpotency class. In particular, this implies that G is solvable. So while not all groups of prime power order are abelian, they can all, in all of them you can find a subnormal series so that the quotients are abelian. And not only that, you can find a subnormal series by continually taking centers and then centers of quotients. And you're guaranteed to get all the way to the whole group. That's what this statement is saying. And you only have to do this at most n minus 1 times. Alright, so we're going to prove this result by induction on n. And we're going to use some of the stuff we know about Pgroups. So it's worth pointing out, you construct the upper central series. This thing always exists in general. And so if zi of g is not equal to all of g, then you can certainly take this quotient, and it's a P-group. Moreover, by theorems we've had before, it has to have a non-trivial center. And in fact, that means it has to have at least p elements. And since that center is how we define the next group in the sequence, that means that the next group in the sequence well, let me do it more carefully. That means that this quotient has to have at least p elements, which means that zi plus 1 of g has at least p times as many elements as zi of g. Whenever I is not equal, whenever the ith central group is not equal to g. So if your group is not abelian, then you should expect to find that Z2 of G has p times as many elements as the center, and so on and so forth. In particular, this implies that we have to have at least p to the I times the number of elements in the center. And since there has to be at least I plus I p elements in the center itself, that means you have to get at least I plus 1 elements. So note, that means that in the worst case scenario, you could have zi is equal to g for I less than n, which would imply that you're nilpotent, g is nilpotent. With nilpotency class n minus 1. Or you're going to end up in the case where z sub n of g has exactly p to the n elements, which means z sub n of g is also g. In this latter case, we're also, of course, assuming that z sub I of g is not equal to g for I less than n. Note, in this bad case, z sub I of g has exactly p to the I elements for all I. So the remarkable part of the theorem isn't just that you have nilpotency, it's that this particular case doesn't actually happen. And the problem here is then z of n minus 2, g, has p to the n minus 2 elements. So when you take that quotient, it has order p squared. All groups of order p squared are abelian. Which means that the center at that point is the whole group. Which tells you that Zn minus 1 of G is G. So the point is, in the worst case scenario where you keep getting increasing powers of I for each of the centers by the appropriate amount, exactly 1 power of P, you actually terminate at n minus 1 because of this fact. So this part's a bit more technical, but it tells you that not only are P groups nilpotent, but if you're looking at the central series, there's going to be at least one pair of consecutive terms in the series whose quotient is a P group that's not a cyclic, or that is not a trivial P group. So it has some sort of higher power than just 1. In particular, that would have told you in advance that the nilpotency class of D8 must be 1 or 2. And since it's non-abelian, that immediately would have told you it had to be 2. So you would have been able to figure out the length of the sequence before we even calculated it. Same reasoning applies to the quaternion group. It must be 1 or 2. Because the quaternion group is non-abelian, it must be 2. So without even figuring out what it is, we already know the answer. So then you could actually figure out what it is. It must be 2, so you must look at the center. The center of the quaternion group is 1, -1. And so then that's it. And yes, you can check the quotient of Q8 by its center, you might recall, is the Klein 4 group, Z2 cross C2, which is abelian. So yes, it's definitely nilpotency class 2.